So thank you everyone for making time to come along again this month. So this month is one I've been looking forward to for a while now, PassivHaus and Retrofit. And thank you to our speakers for coming together quite lately in the process. I'll just start with acknowledgement of country. So just wanted to acknowledge the fact that we're meeting on the lands of Indigenous peoples, the Woiwurrung and Wurundjeri people. Pay our respects to their elders past and present, and particularly in the context of the university emerging. So these proceedings are in the spirit of reconciliation, and may we get there. We've got some great speakers today. We've got a great mix of people. We've got an architect, an engineer, a contractor, a builder, and people from peak bodies in the PassivHaus Association. So PassivHaus is good practice anyway, and it's great, the thing we should be aiming for in all buildings, and it gets to be quite intimidating when you're dealing with an existing building that you're retrofitting. So hopefully today we can hear some stories of exactly what the background to PassivHaus is and the intention, how easy or hard it is to do in retrofit situations. Easier than it sounds is what I'm told. So we have some people with real experience and some real case examples to talk through. I think we'll start with, I'll ask each speaker to introduce themselves, just because I know people have dual roles in some cases. So we might start with Jane and Dylan from PassivHaus Association.
I'm a member of the Australian PassivHaus Association and also on the PassivHaus Association Retrofit Committee. I'm an architect and also a PassivHaus designer.
My name's Dylan, also part of the Retrofit Committee with Australian PassivHaus Association, and registered building practitioner focused on deep energy retrofits, turning existing buildings into passive houses.
We might, Melissa and Eben, we might wait until you guys are ready to speak to do your introduction. So I might let Jane, do you want to start sharing your screen?
PassivHaus explained in 90 seconds. Does your house have a heater in the basement or maybe a fireplace? Probably also a central air conditioner or maybe a window unit. Did you ever wonder if it was necessary? In 1991, a physicist in Austria, Dr. Feist, built the first passive house. Here's what he did. 1. Proper insulation. It's just like wearing the right winter jacket, it also doesn't need a heater. 2. No air leakages. There should be no holes, small or large, to let hot air out of the house. 3. No thermal bridges. A thermal bridge is like a road for heating energy in which warmth can travel right through your walls. As a matter of fact, most of our houses have thermal highways in our walls where heat can easily travel to the outside. Plus, the house needs proper windows most of the time with triple pane glass. It needs to be oriented properly so the sun can heat it in the winter and shade is provided in the summer. And it uses an HRV, a device that provides the inside with fresh air without letting the heat out. Add all these things up, and it turns out your house doesn't need a heater or air conditioner. So where does the heat come from? A passive house needs 90% less energy, and that can easily be supplied by your body heat, the sun, your appliances, light bulbs, and even your TV. This saves you a lot of money on your heating bill and helps preserve the environment. Did we make it in 90 seconds? You bet we did.
Great. All right, thank you. Before I start my presentation, I'll just say that video is a little bit European centric. It would be very unusual for a passive house consultant to recommend no heating or cooling. In Australia, they'd highly recommend some cooling. Correct me if you think I'm saying something incorrect there. First of all, thank you for inviting us today to speak about PassivHaus, in particular Retrofit, as we're both members of the Australian PassivHaus Association. We are also on the PassivHaus Association Retrofit Committee, which is a group of builders, architects, building designers, engineers, ESD consultants coming together with all the shared experience to try and push retrofitting become more commonplace out there. The presentation we're presenting today was originally put together by Lyndon Thornley, who is the co-chair of that committee, but we have condensed a 40-minute presentation down to 50 minutes. Hopefully we've kept the key points in for you. Today we'll cover why retrofitting is important, an overview of a passive house retrofitting, the certification process, how to approach a retrofit, along with some case studies. Next slide. Here's a reminder why we need to be considering retrofit. We all know why. We've got an energy crisis. That sounds like a bit of a 1980s term, doesn't it? But we've got 2050 net zero targets. We've got the Paris Agreement, and retrofitting is a key component for us to get to those targets. Passive House is focused on low operational carbon, whereas when you introduce retrofitting, it's looking at low operational and low embodied carbon, because we all know if we do a really deep retrofit, we can save up to 70% of embodied carbon over the life cycle of that project. And there's not only environmental benefits, there's also social, cultural, and historical advantages as well.
Right. Okay, folks, so we're talking a little bit more about sort of Passive House from a macro sense and how we apply that to existing buildings, being part of the retrofit forum. So Passive House is essentially a voluntary international building standard. It has extremely strict guidelines with regards to energy use and the occupants' health and comfort. It is site and climate specific, very much like you wouldn't go hiking in Wilson's Prom with a negative 35-degree sleeping bag. You wouldn't build a passive house that was designed for Germany in Australia. So it's a bit of a common misconception that it's just for Europe. That's just completely false. What we're building in Australia is completely different. The retrofit standard is known as Enefit. There is some slight differences from new build to retrofits. You've got a little bit of leniency with your air changes. So there's 1 air change per hour as opposed to 0.6. And essentially that's your entire volume of air changing per hour under 50 pascals of pressure. And there's a little bit more leniency with the heating and cooling metrics as well. Continuous thermal insulation is very important. Usually Melbourne's climate's 140 mil walls, or about an R4. Again, Germany, you probably double that, so very, very different. You've got reduced or eliminated thermal bridges. So really good for kind of not losing energy in or out of that building, but also good to eliminate any condensation risk build up in the building envelope. If you think about a cold beer, if you pull it out of the fridge, quickly gets covered in condensation. That's not coming from the beer. It's coming from the water vapor that's in the air. So if you've got a cold point in your building envelope, you're going to have the exact same thing happening. High performance windows and doors. And then, of course, the heat recovery ventilation system, which is like having your windows open 24/7, but without losing that heat that's in the building. It's also filtering the pollen and dust when it's bringing that air in. A little bit about the certification process. So with regards to retrofit, generally we'll do an early assessment of the existing building. So we usually put the blower door on the existing house, which is a fun exercise to show clients, that when they've got their heaters on, they're heating up the neighbourhood, not their house, just because of how leaky our buildings are in Australia. We'll then sort of put together a few different scenarios, and the PHPP modelling tool is great to kind of flush out what's going to make sense from a cost point of view. And then we'll step through some documentation, which will then get reviewed by a third-party certifier. Now, we're a big advocate for getting all the buildings certified. It's just good to be able to give to the client sort of that assurance that it's getting third-party checked. Make sure the builder or the passive house designer hasn't put a foot out somewhere, and it just gives that client the absolute surety that what's been designed has been delivered to what they're paying for. Once we sort of go through that certification process, there's a lot of photos. There's about 300 photos that we've got to supply. The air tightness test as well. So super, super stringent. But once you understand the methodology, it is very simple to apply to new builds or retrofits. There are a few different approaches to retrofit, a few different pathways for Passive House. We've got sort of an internal retrofit, which would make sense for a heritage listed building. You've got an external retrofit, which maybe it makes sense. You've got a building where the internal finishes aren't too old or they're not at end of life, when you can just do the exterior of the building. Or you've got a hybrid of both as well. There's also, single stage or multi-stage. So you don't have to do all the work at once on some particular projects. It's just important to make sure that if there is some early air tightness happening, include the HRV in those early stages as well. And it can be applied to a single house or high density, really adaptable. So there's one case study here, which is the Cali Deep retrofit. This is an example of a interior kind of fit out, and there was some also sort of some feasibility around what options to go with. So you can see there's sort of exterior wrap of wood fibre proposed. There's some blow-in cavity fill, and exactly how that translates to the energy demand. Now, this can be a great tool to show the client, say, hey, we can spend 20 grand on a cavity fill and you'll save $50 in energy per year, or we exclude that and just do the wood fibre. They've just got the data to use right early in the project, which is really valuable. Some tricky aspects when you're dealing with existing buildings, having the right team, the orchestra. This isn't a sort of one-man band operation. It has to be client generally on board, the builder, the architect, talking early on in that early feasibility stage, what makes sense, what's going to stack up from a cost point of view, what's going to be less laborious. There's a lot of kind of questions that pop up in those early stages, and that'll drive or help drive and curate the rest of the design detailing, and really set up the project for success. Continuity of insulation, obviously with masonry buildings, there's a lot of, sometimes there can be internal brick walls that need to be dealt with. So, or getting to the back of stud frames that aren't insulated, those sorts of things. The window detailing can be a little bit tricky. Bringing windows back into the insulation layer can create some externally deep reveals that have to be dealt with, things like that. And air tightness. Obviously, there's kilometres of tape and staples and wrap and labour that goes into making existing house airtight, so that can be a little bit challenging. The thermal bridging aspects, we're sort of okay. I feel like in Melbourne's climate, there's not a lot of sort of cantilevered balconies in the residential space anyway that could cause huge dramas. Certainly in commercial retrofits, that might be a bit more challenging. And the ventilation, where we're running kind of all those existing, or the HRV ductwork, they're uninsulated ductwork, so they've got to be on the inside of the air tightness and insulation layers. Also really important to consider WUFI calculations. It's a high growth thermal modelling, so it's essentially going to tell you where the dew point is in a wall assembly, to make sure wherever you're putting the air tightness layer or the insulation, you're not going to cause build up or a cold point that gets below 9 degrees and you have that condensation happening. And then, obviously there's also a huge risk with a shallow retrofit. So we always advocate for PassivHaus standard, or at least applying all of the principles in a holistic manner. If we go and make the house airtight and insulate it, but not bring in fresh filtered outdoor air, there is a risk of condensation buildup. So there's lots of examples of this: leaky building syndrome in New Zealand, the condo crisis in Canada. We can certainly learn from all those mistakes, or we can make the same mistakes and then go in and redo all the retrofit work, which is what we don't want to do. Aim for that higher level, de-risks a lot of rework in future. And then, there's a project here, the Garden House. This is Lyndon Thorne, the architects. So this is a project where the internal approach was applied. There was, end result, I suppose, the building is exporting more energy than it's using. And sitting between 21 and 23 degrees Celsius most of the time, with really little to no heating in winter and no cooling in summer. This project here is a 1950s weatherboard cottage. This one's a little bit close to my heart. My wife and I took on this project in 2021. Why this house? Put bluntly, it was all we could afford. But it was run down. The inside and outside the building were at end of life, so it made sense for the hybrid approach here that we're going to pull both off. It was okay structurally. So yeah, after I learned about PassivHaus and Retrofit, that sort of a light bulb moment started, and that's when I began Alwyn Projects, our business. Found it really difficult to sort of get a client on board to use us for our first project, so we decided to do it ourselves. The project got a lot of kind of media attention. It was on Grand Design's Transformations, if anyone wants to check it out. Season 1, episode 8. I watch it most evenings. And then, when we pulled the house apart, which obviously retained a lot of the existing materials, weatherboards, timbers, and things like that, and reused back in the project. Externally, we sort of stripped it back, added wood fibre insulation. Obviously, most stud frames in Melbourne is a 90mm, which isn't enough to get the thermal performance that PassivHaus demands. So we added 60mm of wood fibre externally, and then add wraps and the cladding back on. And then internally, high performance windows, insulated the rafter joists, BRO and stud cavities, and then installed internally tightness membranes, and of course the heat recovery ventilation system. The end result is a beautiful, comfortable house, which was quite a huge difference to what it was previously. And we noticed, we lived in this home for about 1.5 years after it was completed. The only reason we sold it was so we could go into another passive house. But some supplementary benefits that wasn't at front of mind. I found I was sleeping better because there was no sound pollution coming from the freeway behind us. We didn't get sick at all when we lived in the building. In fact, after 2 weeks after we moved out, we both fell ill, which was quite funny. There's no hay fever symptoms. The HRV filters all the pollen out of the air, so it's a bad spring day like it is today. I was sneezing on the way in here. I'd just go into the house and within half an hour all the symptoms are subdued. There was less dusting because you've got that dust getting blown in, and no spiders or insects as well, which is a plus. Okay, that's enough from me. Over to you, Jane, for some.
Thank you for your entertaining grand designs comment. Gave me a bit of a chuckle. High performance deep energy retrofits are becoming increasingly common worldwide, including in the multi-residential space. And we would love, or me personally, and a lot of other people would love to see that same trend happening locally, including here in Melbourne. I just want to go through some precedents around the world. So this is the Ken Sobel Tower in Toronto. It's by Era Architects. It's the tallest certified retrofit in the world. This building was at its end of its life, so it was ripe for retrofit, and it was more cost effective to do a retrofit rather than a knockdown and rebuild. The exterior was wrapped in rock wool, services were upgraded, and NVHR installed, and there were some aesthetical improvements as well. Here we have another project. This one is in Manchester in the UK by architects Chu E Architects, and this one focused on external wrapping, and it achieved minimal disruptions to the interiors. I'm not sure if the tenants had to move out or not. This one's another one. So this is in this one is in New York, in Brooklyn. So this is by Henson Architecture. They retained the heritage facade, and upgrades were focused on the interiors. So they did it apartment by apartment. And then this one is closer to home. So this is the developers who are developing 2 projects for build to rent. So the developers are called Model. And this one is a change of use. So this is the old Effervescence factory, which they're changing into 180 residential units. So this one is one to keep your eye on. And now I'm just going to do a super condensed version of a case study that was created by Lyndon Thornley, the co-chair of the PassivHaus Retrofit Forum, along with Advanced Sustainable Architecture and some other people. They put this case study together and presented it last year at the PassivHaus conference. It's basically a deep retrofit for a walk-up apartment block in Sydney, in Camperdown, but these are all over the place. They're in Melbourne, lots of different areas around the country. So the advantage of this particular project is that the floor plate was simple, the floor plans were repeated, it's compact, it's well scaled, it's a very solid construction of being concrete and brick, and it had the potential to increase the yield by doing 2 additional stories in a lightweight construction. The challenges included accessibility issues, low ceilings, basically thermally massive, being concrete and brick, so lots of thermal bridges, so to speak. They had windows that were poor performing and poor ventilation. There was mold, condensation issues, and the heat and cooling costs were high. So basically, they looked at 4 variations. So variation number 1 is business as usual scenario, so not variant 1 and 2. So these were designed to achieve passive house benefit standards through air tightness and a HRV system, along with solar panels, high performance windows, and a reverse cycling air conditioning heat pumps. So variant 1 looks at insulating the brick cavity with a new roof, whilst variation 2 is insulating the external walls and roof, whilst variant 3 is the same as variant 2, but using biomass materials. So the thermal bridges were modelled and all the dew points were calculated and mitigated accordingly. Double glazing with UPVC frames proved to be the most optimal balance of performance, cost and viability. They were looking at compact reverse cycle air conditioning units, which are efficient for heat and cooling and humidity, and they'd be half the size as what you'd expect in an apartment these sizes, I should say. They had a centralised HRV supplying filtered fresh air to all the living and sleeping areas whilst extracting from the kitchens and bathrooms. The HRV allows for a well-sealed, high-performance windows without mould issues, with modest upfront costs and straightforward servicing. Basically, with variant 2 and 3, these are the only overclad options. They achieve passive house benefit performance. So by moving the bricks inside and shading it, shifted the peak load from winter nights to summer days. So basically, they also stress tested it. So with climate stress tests at 2 degrees and 4 degrees, so variant 2 and 3 still met the benefit standard. The windows proved to be the biggest impact. So this cut the heat and cooling needs by 48% compared to the existing building, whilst the insulation added a further 45 to 58% reduction. They also conducted a 50-year life cycle assessment of the different upgrade schemes, examining the embodied carbon of windows, insulation, roofing, and mechanical systems. And the benefit retrofit is predicted to use 94.8% less annual energy than a window-only upgrade to maintain 20 to 25 degrees. So the additional material carbon investment is paid back in just 2.5 years. A cost estimate was carried out for each variant to assess its financial viability. So simply put, more expensive upgrades require higher capital investment, which is... and then they looked at the payback. So when considering the construction payback along with the energy savings, the higher upfront cost of extensive retrofitting provides greater long-term financial security. And this graph shows that over 50 years, these retrofits significantly reduce energy costs compared to a build as usual variant. Just to conclude, the private residential space is certainly leading the way when it comes to benefit. However, we need to acknowledge those that came before us, including this building, which is the Monash University's, I think it's Building 56, otherwise known as 30 Research Way, which was completed by McGlash and Everest in 2016. But equally significant, we have Lovell, Chen, who are pioneers in the use of the Passive House planning package for heritage projects. And they successfully retrofitted historical buildings, achieving high thermal performance and reduce any consumptions, including the Old Quadrant project, which they will now talk to us about. So I'll hand it over to you guys. Thank you.
I'm Milica Tumbas, a principal of architecture at Lovell Chen, involved with most of our retrofit, benefit, and passive house projects. Really, one of the most complex projects was All Quad and retrofitting All Quad. So I'll start sharing. I will share this presentation with Eben, who was responsible for the passive house, PHPP, mechanical, and services in general on this project, and working with us, with his team at the time.
And the team at the time under, we were
UMLI,
but we're now called Introba. But I'll talk to you a little bit about Benefit and the services a little bit later into the presentation.
All Quad, Melbourne University was established in 1853, and the first building to be built on site was All Quad. That was built, the construction started in 1854, and the northern wing was the All Quad was completed. The first north wing was completed in 1857. Following that, there were a number of alterations to the building until 1981, and we completed this project in 2019, with, unfortunately, the last phase ended up in 2020, with a lot of issues with getting access to the site and builder being able to rectify the defects. So it was a really unfortunate period for all involved in the project. It's a significant project for a number of reasons. For architectural significance, it's an oldest non-ecclesiastic Gothic revival building. Its original design for not only teaching, but also for professors to live on the campus, which really fostered social experience in working with the students in a close way. Also, that intellectual interaction between the students and professors was very important. It's a very significant building. It's registered. It's on a Victorian Heritage Register. It's also on a Heritage Overlay. And we had to go through a rigorous process of getting the permit for all of the works. We've consulted with Heritage Victoria along the way, and there were permits, amendments to the permits, also investigative work that required either permit or exemption. So it was a very detailed process, but we had enormous help from Heritage Victoria guiding us through the process and enabling us to complete the project. It was a very complex project, involved part of the building, northern wing, annex, and east wing. So it was the refurbishment of these areas with different approach to the building depending on the wings. The main objective was to re-establish the old quad as the ceremonial and engagement hub of the campus as it was originally. And I think you probably had an opportunity to visit the building. We think that was really achieved. We had also included conservation of the original fabric, details and features, a reinstatement of the original planning where possible, seismic strengthening, fire separation, services upgrades, sprinkler protection, and applied benefit standard and Green Star pathway. So we had to work in parallel to make sure we meet these requirements. The building has three distinct areas, which is the northern wing, where we have re-established the original plan and also the original floor levels. The building over time got divided into 3 levels. Originally, it had 2. So we have brought back that original planning and original floor composition. And established the envelope. We had to exclude some of the areas like the toilets, the central stair, and the commercial reheat kitchen. That is not part of the NFIT envelope. Establish the clear lines so that each area can be assessed on its own. And the approach was such that all of these areas have a different construction, the methodology, different thickness of the walls, and different level of details. So where we had in the northern wing, where we had the opportunity to re-level the building or remove the non-original levels, we had a lot more freedom to do full NFIT retrofit. And in the other areas, we took a different approach because there was quite elaborate library that we had to bring back to its own, to the original. So these areas here, they are designed as NFIT. And the east wing, we introduced the internal insulation, but with a lot less ability to do the full NFIT. So this is the building, interior of the building before any work started. And looking at this, we had a vision for something else, a lot more closer to the period of the building. The construction started, a lot of surprises under the subfloor construction, and part of the NFIT approach and mechanical services was to construct a subfloor space. So part of the mechanical services come from the floor and part from the roof. Thanks to UMLI, we were able to eliminate a need for a huge chiller. And Eben is going to talk about that a bit later. Then the building the northern wing was aligned with SIP panels in this instance. We had a permit to use the SIPs in this particular application, and there is a clear delineation between the original building and the new walls with fully ventilated cavity so that there is no condensation. And if there is any condensation on the original walls, that would go down into a channel and then drain through the subfloor space. Blood test a number of times. And this is the northern wing, some of the
Presenter is
space
terrible.
that are very close to that vision that we had at the beginning. This is University Hall, which is on level above, and you can see the windows here. We were not able to, apart from restoring the original windows and replace broken glass, we were not able to do major alteration or to change the glazing to double glazing. Just the windows are so fine that there wasn't an opportunity to do that. And we did internal windows. And each of the windows are actually vented as well because of that possibility that we get the condensation on the windows and create moisture within the windows. So each of them are ventilated separately. The library, this is an original it's a photograph from 1901 of the library from the University of Melbourne archives. It was completely altered for teaching purposes, and it lost that grandeur that it had originally. We decided to strip it completely to its own original shape. And this was the vision to actually return it back to what it was. We've taken a different approach. The roof is fully insulated, multiple layers. The services are running concealed, so the sprinklers, apart from the light fittings, the services are concealed, fully respecting the original ceiling. The walls were lined with a proper gap between the original walls and the new linings. The new windows been installed, slightly different detailing than in northern wing because it's just a different construction, different thickness of the wall, and different objective for this space. And now this is constructed, and it's really brought back to its own, to the original design. We did a paint analysis, found that very blue-gray paint color and the original color, and that was replicated here. East wing, we had a limited opportunity, and it was a limited scope there because that was the first phase of the East wing restoration, which then continued on. And just I'll invite.
Thank you,
to-
Milica. Yeah, so obviously what you've seen there is pretty amazing for a heritage listed building, and the main way that we were able to actually reduce the size and control the energy efficiency was due to the fact that Lovell Chen created this highly insulated sort of internal portion of the building that separated it from the heritage external facade. On the screen are some of the bits of data around some of the air conditioning in there. So the way that we managed to control the building, this building was gas boiler fed, drafty, old, had radiators in it, didn't need a lot of cooling, needed a lot of heating. When you actually go through the PassivHaus Retrofit thermal envelope design process, you convert what was a very thermally massive, heavyweight cold building into quite a lightweight, really nice and warm building. Effectively, what that does is give us a shift, like in the earlier presentation, between needing to think more about heating to thinking a little bit about how we temper the air and how we control cooling. In a PassivHaus environment, it's very easy to eliminate heating, but in this particular building, we've got some of the great halls, which have got 200-300 people capacity in that. If we load up those halls with all of those bodies in a confined space, they produce a lot of heat, and part of that needs to be considered still within the PassivHaus envelope. So some of the techniques that we used to achieve that, as you see, these are very tall spaces. So number one was air distribution. So all the air distribution that comes through into the spaces, we have ducts hidden inside the walls to inject the air at low level. We call that displacement ventilation. And in some areas, we use that floor zone, which is called underfloor air distribution. So what that enables us to do is, instead of having to look at the entire air volume of that space, we can just look at the occupied portion of that space, the first 1.5 meters, 1.8 meters where everyone's sitting, and we just worry about climate controlling that component of the space. Because this space is so heavily insulated, what we're always thinking about is just injecting a small amount of cool air when those spaces are busy. And in Melbourne climate, for a large portion of the year, we have a lot of free cooling that comes in there. When we don't have free cooling available, what we used was pre-cooling of the outside air using indirect evaporative coolers. So if you're used to a swampy unit in your house, that will be a direct evaporative cooler, and that's putting moisture in the air and that's blowing into your house. We don't want that in a building such as this, because we create extra humidity and more discomfort. So what we did is you inject all that moist air in the exhaust air stream, and it goes through a heat exchanger, and that cooled heat exchanger pre-cools the incoming air. So that was our first stage, and then we used heat exchangers. As you see, we were pretty short and tight on space. We had to work within the space that we have available. We actually used plate heat exchangers. They're 75% efficient. If we had more space and more room to deal with, we might have put in thermal wheel rotary heat exchangers, which give us an extra 10%, or what you commonly see in whole house ventilation is regenerative heat exchangers. Now, those passing the airstream over the same surface, they can be about 95% efficient. So what that means is 95% of that heat that's going out of your house or your space is reclaimed, coming back in. So that's the most efficient that you can possibly have. But obviously, working within an existing building, we are more constrained. Go to the next slide. What we looked at there in terms of the whole energy of the building, we are asked to look at its raw energy efficiency. And in terms of going through that primary energy demand, we go through the end effect calculation, came out with a 65 for that aspect, and we complied with the end effect requirement in that respect. And then we'll go on to next. And this is a snapshot of the end effect calculation. So what you can see there is we achieved, as you sort of work down from the top, the bottom bit is the component retrofit component, that bottom rectangle there, and the top part is like the full passive house component. We didn't go through and rate on that absolute top bit there. We got very close on the heating demand at 17, 15 is the component there, but through the thermal envelope, we managed to full and effect compliance. So we got to 0.9 air changes an hour of air leakage, which for such a big building is a pretty good achievement. To put it in context, you know, a standard build house might leak, 20 air changes an hour, 25 air changes an hour. So if you're in a house in the 1980s, don't be too surprised if that's how much air leakage is going through your house. So to get down to 0.9 was very good. Full passive house on new buildings, 0.6. So we got very close. And then as you go through there, you can see how we were able to work with Lovell Chen and with the secondary glazing that went in there, and within creating this space within a space, we were able to meet all of the thermal envelope requirements. So I can't stress enough that to make sure that a building requires the least amount of heating and cooling, it's all fully reliant on a really good thermal envelope. And I'll just add at this point that passive house is a process and a methodology. So it's not just about the testing at the end. And I think, in terms of the builders talking through that, there is a process of working through looking at the details and getting the details right so that they can be built to be airtight. And then there's a whole process as we go through the building of inspecting before we close up elements and making sure that that install has been constructed to a high standard. When you get to the airtightness test at the end, it's really the icing on the cake, all right? It's just proving that all that hard work that you've done going through the process was validated. And that's what the airtightness test is for. In early passive house, everyone kind of focused on that and forgot the process on the way through. So if you follow the passive house methodology, it's a repeatable methodology, it's highly effective methodology, and it continuously gives you really good results. I'll hand over to you to finish. Yeah.
Thank you. This is the east wing, some photos before the retrofit, during construction, and finish on the right-hand side. Dylan touched on the.
Any more slides?
This is the last one.
Okay, no worries.
Dylan talks about key components to be able to achieve passive house and achieve successful project. And this is a little bit more extended list. So it's informed and committed client, which in this case, we had a wonderful client, right consultancy team, which we managed to get some amazing consultants that nothing was difficult and everyone was on the same page. We did heat and moisture transport modeling using Woofy, but on other projects we used other programs as well. Depends on which project the clients, the consultants preferred. Cost plan, so the QS building surveyor were on board from day one. there needs to be sufficient time for consultation, for documentation, because documentation is a lot more comprehensive than the buildings that are not Enefit or PassivHaus. We had great suppliers, very supportive, familiar with PassivHaus. Then we developed a specification because it's slightly different, and there are components that are different than just the standard specification. So we had to address Enefit and particularly how the air tightness is performed, QA on the project. Developed a risk management plan. Then had the project managers and superintendent roles is really important, so that there is a full understanding and support behind the team. Sometimes on site, there are decisions to be made that might be a bit more costly, and we had a support in achieving that.
Yes, I might ask you just to finish there, because I think there's people will see this and go through it, but also want people to give them the chance to ask a question or two as well.
Yeah.
If you wouldn't mind just stopping sharing, and I might take over and just quickly do what's happening around the traps in Retrofit on what's happening. So there's a public meeting coming up on the 23rd of October, 6 p.m. at the Capitol Theatre. It's being coordinated by Kate Shaw from the Geography Department here, and I think it's an official name is enough with an exclamation mark, and it's really a pushback about not enough happening on public housing, and in particular the towers. So there'll be a number of speakers around the process that was gone through with the public housing towers, and what the opportunities or alternatives are. So it's really a call to action on retrofit in terms of housing. There's the Melbourne Build Expo 2025, Melbourne Convention and Exhibition Centre, also on the 23rd of October. So there'll be lots of stuff in there, hopefully on retrofit as well. The other one that wasn't on here that I thought I'd put in was just a reminder that the class action on the housing towers is going back to appeal, I think, on the 27th of October in Red Court. But if you Google search housing tower inquiry and the appeals process, it'll pop up details of how you can actually go to see that court hearing happen. So many questions out of those presentations, and I really wanted to let them run because there's so much good content in there. Of course, if people need to go, please feel free to leave or to sign off if you're online. But I think we'll continue with some questions for those who want to stay around and just listen and ask. So I might start. Actually, I'll start with one for you, Dylan, which was one online from Barbara, I think it was, which was about costs. So being the owner and the builder at the same time, I'm pretty sure you had a good grip on the costs. So could I ask you, was it more expensive, and would it, in hindsight, how does it compare to rebuilding it again? And I guess the second question to that is it a different answer now than it was back then? Are you learning stuff along the way?
Certainly there was a lot more labour involved than initially thought out, but yeah, getting up into the attic space after the project's completed, it's all vacuum cleaned and perfect temperature, and all the hard labour just quickly gets forgotten about when you're in this kind of perfect environment. So I think cost is one that pops up quite a bit, especially in early feasibility, but the benefits that you sort of get just outweigh them quite quickly. And when you're comparing sort of an architectural project to a passive house project, the cost can be quite similar. We work with an estimator who works with maybe 8 or 9 other architectural builders. We're the only sort of passive house retrofit builder, and we're sort of middle of the range as far as square meterage costs. So it goes to show it doesn't have to be more expensive. It's just certainly comparing it to a volume built house, it's going to be a bit different, but to architectural projects, I think it's.
I guess it's what you're purchasing, isn't it? So the idea of a dust-free, spider-free environment is pretty attractive to me. So, I live in a 60s house and we have a lot of spiders and a lot of dust. Yeah. Look, I'll just jump in with the second question just because it's on my mind, which is really to Melissa and even on the old quad. When I look at those drawings and sections and displacement, ventilation and those, I mean, they're not unusual things that you wouldn't expect to see in other, you know, commercial high-end type developments. Is that your feeling? Was it about the detailing, or is it actually just fundamentally different to other projects that you work on that are passive house, other retrofit projects and all?
I think, I mean, a lot of it's around the architecture. I mean, it was maintaining, you know, the heritage overlay in that building and achieving that insulated thermal envelope within the other building. That's no mean feat to do. The air conditioning approach isn't new. PassivHaus uses standard practice, ready available materials that can be applied anywhere. It's just what we're doing with getting the thermal envelope sorted out and the controlling and eliminating those loads out of the equation. All of the size of those ventilation systems and cooling and heating systems, in some cases heating goes to nothing, and that's the outcome that you're looking for. Certainly in Australian climate, in Melbourne climate, is to get to a zero heating energy outcome, and then you're trimming the cooling to the absolute minimum. So the displacement was necessary because of the height of the space. If you had a lower ceiling height, that component of how you might manage that, and I'm saying the only reason you need it is if you've got a high people density or something else like that. You know, in most houses, you don't have that density. Most of the time, you won't even need to use cooling. Have to just stress that. But it's about controlling the size of that. And what I'd also say about the cost is, you know, since, I mean, in mid-2000s, 2010, trying to get hold of double glazing, or 2004, I can remember talking about double glazing and just getting laughed at as if I was from a different planet, going, that's going to be 2 thermal envelopes. You know, it's like, what are you talking about? So much cost. But as more people adopt better practices, there's economies of scale that come through. So we have a much greater palette, if you like, of materiality that's high performance over here, readily available, being manufactured in Australia now. We can get airtight windows, you know, timber, low carbon manufacture. That's sort of come here. We've finally got manufacturers that are rating those components to standards for PassivHaus now that we didn't have before. And if you look at how that establishes itself, and I went on a study trip to Germany, and that was around about 2011, 2012. And the interesting thing there was they're so used to putting double glazing and triple glazing in a building. They had an internal atrium where they wanted some of the energy to seep into that atrium from the conditioned spaces. So they only wanted single glazing, but it was actually more expensive for them to purchase single glazing than it was for double glazing. So I think, you know, as more people adopt these better design practices, the cost comes down further and further and further. And then I think it's fair to say every time I speak to a builder that's gone through a PassivHaus process or a contractor and understands how it works, they never want to go back to building in any other way, you know, and it's there, and it's a methodology that's readily available, it's proven, repeatable. So obviously I'm quite a convert So I'm sure you've got something to add on that.
From the architectural point of view, what we managed to do together is to hide mechanical services. You don't see them. You see odd grills, as you would, but kept the volumes of the spaces at maximum. I mentioned the chiller, because the first calculations came without retrofitting. A huge chiller had to be housed somewhere, either on one of the buildings or somewhere on the ground, with a huge heritage impact on the site. So that objective was minimal impact on the original building or on the site, which is on overlay, and making sure that and we used tricks like under the floor, the roof, space in between the floors, created a separate plant above the commercial reheat kitchen, and it's basically you're not conscious of the mechanical system or see.
Trying to just minimize it to the absolute minimum. You know, the desirable outcome is you don't really need air conditioning. You know, that's what you're trying to get to, but we have to have air to breathe and things like that. And you can have openable windows in Passive House. They just feel, the Institute, that there's more error. If you open a window at the wrong time, you get drafts and you get a lot of, you can add to the energy rather than take it away. So that's why there's always this focus on having a background ventilation system that's always running, and it gives you all those other air quality benefits as well. So there's lots of other tricks in Alwyn, far too many. I think that we could go into detail here, but
it's an advert for paying for good advice, I think. I mean, it's a great outcome. I've been to events there, and I was quite surprised to hear that it's a Passive House retrofit. So yeah, well done. Open the floor to any other questions if people have them. Yeah.
I think it's rude, but with that great project on the floor, but with the internal wall linings, was there sort of a net loss of floor area? And if that's sort of is there a metric for buildings of that scale as to how much space you lose?
There was, but the spaces are huge, and it still met the requirements and housed the number of people in accordance to the brief.
It's just the sort of question that a commercial operator would be asking in terms of net lettable space. You know, 10 centimetres council.
Yeah, in this particular instance, that wasn't a huge issue. It was discussed during the design and got approved. And that building was gutted because of all of the interventions during a number of years. And we had that opportunity to put an internal wall. We didn't have that opportunity in the other two areas. But this was a great opportunity to achieve the thermal requirements, air tightness requirements, working within the envelope, and detailing around fire rating, seismic bracing, and all of that had to be isolated from the envelope. It was quite complex.
That was, I mean, that Alwyn's pretty unique because it's got that heritage facade. So there was no other option other than to put the insulation on the inside. But depending on the building, you do have the option of reversing that and thinking about putting the insulation on the outside. So there are different approaches that you can take with Passive House, particularly if you're worried about the internal area. But that one, there was no choice. There was we couldn't disrupt the heritage facade. So that's just to give it a bit of context.
And in the northern annex, we didn't have that opportunity. And we had to keep the library very close to the original. There was a different approach without losing that amount of space. So it's basically 200 odd millimeters to the perimeter. The building is not even and parallel, so there were some discrepancies, but on that size and volume, it wasn't an issue.
Are there any other questions around the table?
I might ask one if I can. So I'm from the Municipal Association of Victoria. So we work with the 79 councils from across Victoria. And sorry. So we're working with councils across Victoria to look at the retrofit of their own existing buildings to adapt it to housing, social and affordable housing where possible. So what would it take why wouldn't a council just go for a high energy standard, like a 7-star rating? What's the case to compel them to move to a passive house approach?
I think the risk of having to retrofit that building again in 10 years' time because there's hotter summers or colder winters or more extreme weather events, like you really want to stop the risk of doing the retrofit twice.
Right.
So even though passive house might seem a little bit extreme because of it's quite a niche still in Australia, we really need to look at the end game of net zero. And if we're doing things twice, it's kind of more embodied carbon. It's the energy use that gets locked into that building with the shallow retrofit. So it makes sense just to go the whole lot today, pull the Band-Aid off and go for it. Yeah.
I would certainly agree. I would say, why wouldn't you use international proven standard in passive house and start to apply that here? You know, I would say Australia has a tendency to create bespoke metrics for Australia as if we have a unique climate. Problem when we create bespoke metrics is we create bespoke kind of qualifications and skill sets that aren't necessarily transferable internationally. Whereas if you were to adopt a proven, repeatable standard such as passive house, then you open the affordable housing market to a skill set that's internationally available. So that's number one in terms of doing that. Why doesn't that happen? I watch people almost, there's this worry about cost, or there's this worry about making too big a jump, I think, because if I look at a lot of the bespoke metrics that are introduced, and with a bespoke metric, you have to have a process of somebody there at council needs to understand it and be able to govern it. You know, part of the problem at the moment going through the planning process is, you know, there's not that skill set there and it delays that process and that causes complication, whereas passive house has a process of managing that. But I see like halfway house steps there. NAFAS is a good standard. There's a problem with it. It defaults air tightness. So therefore it would rate a passive house building in a similar way to a non-passive house building because it has a default air leakage. So there is a problem even in the NAFA's rating system, is that it doesn't quite give passive house the credibility and the actual end performance that it really delivers within that scheme. And obviously CSIRO developed that, and it's now dealing with thermal bridges. We've got an optional bit in the regulation that talks about air tightness. You know, after solar loads, air leakage is the biggest thermal load that you experience in any building. It's way bigger than conductivity through a wall or anything else like that. So I haven't really answered your question, probably in the way, but I'm a bit like, why don't we adopt an international standard? and have that wealth of knowledge and have that international manufacturing people that understand it, and they're producing air conditioning or ventilation equipment and windows and things like that around that, because I think that would accelerate performance, which we desperately need in terms of climate change and things like that in this country. That would accelerate the throughput by using an already established successful system.
The only time in there, NATO's ratings are the minimum standard. PassivHaus is the right standard. That's the difference. So if you're going to produce something that is quality, healthy, low cost to run, it's financially viable over a period of time, then as our colleague said, why wouldn't you? If you're driving always to that minimum standard, that's what you do, because that's what people will build to. And if you've got a target that's better, you're going to have a better outcome, and it'll start to float up. As NATO has improved 6, 7, 8 stars, but there are gaps, and it's not as complete, and the process isn't as measurable and repeatable.
Yeah,
Because the climate here in Tasmania, and what we're going to build down there, and we're going to build in Cairns, it's going to be different. But the outcomes is very, very similar, or the same. So it's a methodology that you get to an outcome you're looking for, rather than dumbing it down to a minimum that be different. Well, you know, you understand it's Tassie and one, Brisbane, that's going to be different.
Yeah.
Sorry.
As Sean said, there are gaps, but NCC and NATO's are coming closer to PassivHaus. And in terms of the cost, it's the cost of a bit more of insulation, air tightness membranes with NCC, and quality control. And
it's not expensive, yeah.
it's these 3 items basically that
Can I chip in there with an observation as well, bearing in mind that it's coming from a structural engineer, so it might be wrong. So it's a bit of a question as well. But I was fascinated by your slide, Jane, looking at the different options, and only the options at 3 and 4 actually met benefit standards, and the other 2 you were looking at as well. So when we grade projects like that, it's very easy as a project manager and an engineer and as a client to look at cost and carbon versus effort in and all of those sort of things. And then the thing that seems to come with PassivHaus more is that indoor environmental quality as well. So like you were saying, Dylan, not getting sick and filtering out the pollen and all of these other things. Is it fair to say that that's seen as one of the big advantages of PassivHaus in Europe? And you know, it's the lay public, they're getting used to talking about carbon and cost and energy, but they are going to get more used in the next 5 to 10 years to be talking about indoor environmental quality.
Yeah, I think the early adopters of PassivHaus generally are environmental drivers, and it's about energy efficiency. And then in other countries that have adopted it, the macro uptake, and all countries that have adopted it, there's this huge bell curve. And I think it is generated from the health aspects that the occupant gets from building this way as well. So it sort of needs those, trailblazers to environmental warriors to kick things off. But then when people move into PassivHouses, all they do is scream it from the rooftops of how good's this. And then you see the mass adoption from that health aspect.
So the other big cost factor, the first is, like you say, them having these double glazed units available and all that sort of thing. But the other factor is having the skills out there and having tradies who understand PassivHaus and having builders who understand PassivHaus. So
I think that's, yeah.
Do you get a comment on how that's changing, or how it needs to change, where it needs to be? Or
I think it grows, and when you're introducing a new system, there's a greater chance of error, and there's, certainly we look at builders that have delivered to PassivHaus before, or if they're new, and if they haven't, then we're very attentive at that beginning stage, particularly looking at the detailing and the installation, and how they're applying that when they get going, just to make sure that's correct. It's probably the air tightness bit is the newest bit, but you can expect, again, over time, as more builders understand how to do that, it'll just become commonplace. And that's what happened over in the UK with air tightness. They did a lot of looking at, it's in their part L over there, which is our section J over here. Well, it's not in our section J. They had a stewardship process, and now it's just it's accepted that everyone understands how to do it. So it's just navigating over that sort of that hill to get the skill set up, and then it works. And the important thing here is that presentation at the beginning was talking about triple glazing. You don't need triple glazing here, it's double glazing because we don't have that extreme environment. So those components in there are not a big shift. And as you said, it's like insulation is dirt cheap. It's just thinking carefully about how you put that all together. So
the Training and Education Association is putting out now is a lot of trainings out there at the moment. As I said before, it's floating up.
I think that's an opportunity for a plug, Jane. Where do people go for information on PassivHaus?
Their website.
Their website.
Yeah, so they provide tradesmen's, so they provide the designer course and also tradesmen's course and other courses. You just want to do it like one day short.
PassivHaus.
Yeah, lots of site visits. We've got the
go.
International Open Day coming up. So if you want to see some
Absolutely.
projects in construction and complete, have a look at that.
One question for Dylan, Jay. We have a lot of pushback on the clients on the certification. It's just
Not
adds
this one, no.
to the cost quite substantially on the resident projects, not so much on the
Yeah.
commercial. But it is something that I think the institute needs to think about.
Yeah, no, that's something I find challenging.
It's very challenging. People want to do the works, they want to do the PassivHaus, they're committed.
Yes.
We work with a lot of potential clients, and we do PassivHaus to come forward.
Keep the mobile phone.
Yeah,
It's not
We're
certified.
well over time, but I might just squeeze in one last question, which might bring us up to 5:30.
Just
So
on
we'll leave it on time, we might sort of start there. So this is online from Melbourne. Maybe for you, Eben, this one? What are the pros and cons of having insulation on the inside or the outside? Does it impact vapor management and thermal mass much?
Sorry.
That's all right. So there's a question here probably for you, which is what are the pros and cons of having insulation on the inside or the outside? Does it impact vapor management and thermal mass?
Oh, interesting one. Yes. It depends on the type of building. So yeah, if you put the insulation on the outside, there is a different detailing process, and you are exposing the thermal mass, if there is any, in the existing building, to the inside. So in theory, if you've got a really heavily insulated thermal envelope and you've exposed the thermal mass on the inside, you get a more stable temperature environment. So in theory, that should reduce your reliance on heating and cooling even further. But there's each case is an individual case about whether you can put it on the inside or put it on the outside. Quite often you can run into ground around town planning process in terms of appearance if you put it on the outside. The second thing is about vapor, and we've spoken about something called woofy, and that's all to do with condensation management in inside buildings. So there's a couple of ways you don't need to use woofy. That's WUFI. It's a dynamic condensation analysis piece of software that looks at the drying of a structure and its breathing. You can do a steady state, but the importance there in terms of vapor management is if you look at traditional construction in buildings in Australia, what you will see is you'll see the plasterboard on the inside, even if it's brick veneer, and you'll see a layer of insulation, and then you'll see a vapor barrier membrane holding all the insulation together. Now, when you've got a really air leaky building, where you put that vapor barrier doesn't really matter, because all the moisture that's building up inside the building is just leaking out of the building. That's why it's never mattered in the past, because our buildings are so leaky. When you actually create a really airtight building, you start to lock all that moisture inside the building. So all the moisture is sitting inside. And actually what that means is you need to move the vapor barrier to the inside of the structure in a heating environment, because the moisture is inside. So you've got to stop the moisture leaking into the insulation, and then the insulation sits in a dry environment. If you're up in the tropics, it's the other way around, because all the moisture and humidity is on the outside. So you reverse where that is. But some of the reasons why I think some early passive houses over here didn't quite succeed and didn't work properly was not thinking carefully enough about where that vapor barrier membrane is and how that works, because we've been building so leaky, we never had to think about that before. So whether the insulation's on the outside or the inside is kind of irrelevant, but where you put the vapor barrier in terms of the climate conditions that you're sitting in does matter. You can do it through WFI, you can do it through steady state, make sure it never happens. So I don't know if that was over answering, but there's that's sort of.
Look, I think that brings us up to well, we're well over time, so I really appreciate everybody staying on. So if we could maybe put our hands together for Eben.
Thank
That
you
was
for
a
inviting
great
me.
session. I learned a lot and good comments online as well. So thank you very much. And we'll hopefully see everybody again last Tuesday next month. Thank you.